The universe is a place of breathtaking scale and profound mystery. For centuries, humanity has looked to the stars, wondering if we are truly alone. This question forms the heart of one of the most compelling cosmic enigmas, the Fermi Paradox. Its origin traces back to a lunchtime conversation in 1950, when physicist Enrico Fermi famously posed a simple yet profound question. Where is everybody? Given the age and vastness of the universe and the sheer number of stars, this question immediately highlights a significant paradox. The numbers are staggering. Our galaxy alone contains hundreds of billions of stars. Many of these stars are orbited by planets, with estimates suggesting billions of Earth-like worlds could exist within the Milky Way. These statistics suggest a high probability that life, perhaps even advanced intelligent life, should be common. So, where are the alien megastructures? Where are the interstellar probes? Why have we not detected any definitive signs of extraterrestrial civilizations? This profound absence, despite the statistical likelihood of their existence, is the core of the Fermi Paradox. It's a mystery that has fueled endless speculation, from science fiction narratives to rigorous scientific inquiry. The search for answers forces us to confront fundamental questions about life, intelligence, and our place in the cosmos. Understanding this paradox is not just about finding aliens, it's about understanding ourselves. It challenges our assumptions and compels us to think critically about the conditions necessary for life to thrive and endure across cosmic timescales. Among the many potential solutions to the Fermi paradox, one stands out for its chilling implications: the Great Filter Theory. This theory proposes a central idea. Somewhere along the evolutionary path from simple life to a spacefaring, detectable civilization, there must be an insurmountable obstacle. This obstacle acts as a filter that prevents life's progression. The purpose of this filter is clear. It explains why simple beginnings rarely, if ever, evolve into advanced, detectable civilizations. The filter acts as a bottleneck, ensuring that the universe remains largely silent, at least to our current instruments and understanding. It suggests that the path to becoming an interstellar species is fraught with immense difficulty. The nature of this filter could be diverse. It might manifest as a single, devastatingly rare event or condition. Alternatively, it could be a series of extremely challenging hurdles that most developing biospheres simply cannot overcome. Each step in the evolutionary journey could be far more improbable than we currently imagine. The significance of the Great Filter Theory is immense. It shapes our understanding of our unique place in the cosmos, whether we are incredibly fortunate or tragically doomed. It also profoundly influences how we consider our own future, highlighting potential existential threats we might face. This theory forces us to reflect on the fragility of life and the immense challenges of long-term survival. The Great Filter Theory gains its power and its dread from where this filter might be located in the timeline of universal evolution. There are three primary possibilities, each with vastly different implications for humanity. The filter could be in our past, in our present, or in our future. Each location offers a distinct explanation for the cosmic silence we observe. The first possibility suggests that the Great Filter lies firmly in our past. This means that the most difficult step for life to achieve has already been overcome by humanity. If this is true, then the emergence of life itself is an incredibly rare event, making our existence truly exceptional. The primary reason for this rarity would be the unbelievably specific and unlikely conditions required for abiogenesis. This is the process by which non-living matter gives rise to life. While scientists are making strides in understanding this complex process, it may involve a combination of factors that are scarcely met elsewhere in the universe. Consider the early Earth. The right chemical precursors, energy sources, stable planetary conditions, and protective atmosphere. Each component might have a very low probability of occurring simultaneously and sustainably. If these conditions are indeed unique or exceedingly rare, then life rarely occurs across the cosmos. Under this scenario, we might be one of the few, if not the only example of life that successfully passed this initial formidable hurdle. The outcome is that the universe is largely barren of life, or at least complex life. This would make Earth a precious, incredibly fortunate anomaly. Our existence then becomes a testament to an extraordinary cosmic fluke rather than a common universal outcome. A second possibility places the Great Filter within the complex stages of evolution that lead to intelligent life. This scenario suggests that while simple life might be relatively common, the progression to complex, intelligent, and technologically advanced forms is severely bottlenecked. The filter is an evolutionary bottleneck that most biospheres cannot navigate. There are several potential stages where such a bottleneck could occur. One significant hurdle might be the emergence of multicellular organisms from single-celled life. This transformation was a monumental step on Earth, leading to greater complexity and specialization. It required intricate cellular cooperation and new genetic pathways. Following this, the development of intelligence itself could be an incredibly rare leap. While many species exhibit forms of intelligence, the specific kind that leads to abstract thought, tool-making, and scientific inquiry might be exceptionally uncommon. The cognitive demands and environmental pressures required could be uniquely precise. Finally, the bottleneck could lie in the transition to technological advancement. Even with intelligence, a species must develop the capacity for sustained scientific progress and the engineering skills to build a civilization capable of interstellar communication or travel. This requires a unique blend of cultural, societal, and technological evolution that may be almost impossible to achieve. If the filter lies here, it implies that many planets may host thriving ecosystems, even complex organisms. However, very few ever develop the specific blend of attributes necessary to become a spacefaring civilization. We are currently navigating this part of the filter, striving to overcome its challenges. This third possibility is perhaps the most concerning and chilling. It suggests that the Great Filter lies ahead of us, meaning that advanced civilizations inevitably face a self-destructive force that prevents them from becoming truly interstellar. We have not yet passed this filter, and it awaits us. The implication here is terrifying. Our technological progress, which seems like an indicator of success, could actually be bringing us closer to this existential threat. It means that most, if not all, advanced civilizations develop technologies or societal structures that ultimately lead to their own demise before they can expand into the galaxy. The very capabilities that define an advanced civilization become its undoing. There are several potential self-destructive forces that could act as this future filter. Nuclear war is a prime candidate, as weapons of mass destruction proliferate and global tensions rise. A widespread conflict could easily devastate a planet and its civilization, erasing any chance of interstellar outreach. The ability to destroy ourselves arrived relatively quickly after our ability to split the atom. Environmental collapse is another grave possibility. As civilizations consume resources and impact their home planet, they might inadvertently trigger irreversible climate change, resource depletion, or ecosystem destruction. This could render their planet uninhabitable or severely reduce their population, preventing further development. Our current climate challenges serve as a stark reminder of this potential. Furthermore, demise from advanced technologies themselves poses a threat. Uncontrolled artificial intelligence, runaway nanotechnology, or unforeseen consequences of genetic engineering could all lead to catastrophic outcomes. The very innovations designed to improve life could instead become the agents of its termination. It's a dangerous gamble where the stakes are our very existence. If this future filter is real, it means our current technological progress, our scientific achievements, and our rapid development might not be a sign of our uniqueness or success. Instead, they could be a dangerous gamble, hurrying us towards an inevitable shared fate that has claimed countless civilizations before us. It casts a long shadow over our future, urging caution and responsibility. The Fermi Paradox and the Great Filter Theory force us to confront uncomfortable possibilities about our place in the universe. They challenge our anthropocentric views and compel us to consider scenarios where humanity is either incredibly rare or precariously positioned. The implications for our cosmic destiny are profound, shaping our understanding of survival and progress. If the filter lies behind us, it means humanity is extraordinarily fortunate. The conditions that allowed life to emerge, or complex life to evolve, must have been exceptionally rare, making Earth a truly unique cosmic experiment. This suggests that we might be one of the very few, if not the only, technologically advanced civilizations in our galaxy, or even beyond. Such a realization places an immense value on our existence and calls for guardianship of our singular planetary endowment. However, if the filter lies ahead of us, it raises a chilling prospect. It implies that our current stage of development is not a sign of triumph, but rather a step closer to an almost inevitable collapse. Our survival is then far from guaranteed. It becomes a race against an unknown, yet potentially insurmountable barrier that has extinguished countless civilizations before ours. This possibility compels us to reflect deeply on our actions and priorities as a species. In this context, the search for extraterrestrial intelligence, or SETI, plays a crucial role. Every signal, or lack thereof, contributes to our understanding of the filter's nature. Detecting even a faint whisper from another civilization would offer immense hope, suggesting that the filter is not ahead of us. It would imply that intelligent life can and does overcome the challenges of long-term survival. The silence, conversely, continues to fuel our anxieties. Similarly, our continued exploration of the universe is vital. By studying exoplanets, stellar systems, and cosmic phenomena, we gain critical insights into the conditions that foster or hinder life. This exploration helps us better understand the potential challenges that life faces across the cosmos, from planetary formation to astrophysical events. Understanding these natural filters helps us calibrate our expectations and prepare for potential threats. Ultimately, the Fermi Paradox and the Great Filter serve as powerful reminders of the universe's vastness and profound mystery. They underscore the fact that our understanding of life's prevalence and its trajectory is still in its infancy. The answer to Fermi's question, "Where is everybody?" may hold the key not just to understanding alien life, but to securing our own survival. Our future might depend on correctly identifying the Great Filter wherever it may be.